So first, free body diagram. There's thrust at A, but not at B. So we know that there is a force vector I'm going to do the axes like this. Okay, so there's x-axis, y-axis, z-axis. So I'll call this RA. And then over here at B, there's no thrust. So that means that there's no force applied along the axis of rotation. There's a component that way and a component that way. So I'll call that RB X and RBY, but there's no RBZ. And in this case, because these two pin joints share the same axis of rotation, we don't need those couples. And then the only other load happening is at the center of mass. We have a downward force of 30 times G, so 294.3 newtons. And a tension, yeah, you're right. Okay, so pancake, artist. Row 4, marzipan. The about point you always get to choose. So I'm going to put it at A because we have a whole bunch of unknown forces there, and then they don't show up in the moment equation. You know what I mean? Yeah. But you'd get the same answers no matter where you put the about point. And I'm going to put the origin here at A2. So the force RA is at the origin. The about point is the origin. So the row vector is 0. The force vector is RAX, RAY, RAZ, and there's no moment. And then the weight force, that happens at so 0.24 negative Z, and then 0.24 X. The about point stays the same. So the row vector is 0.24, 0, negative 0.24. Uh-oh. This looks bad. row vector is 0.24, 0, negative 0.24. The force vector is 0, negative 294.30. And can someone calculate that cross product, or has anyone? 70.6? Okay. And then and then the tension force, that's acting at 0.480, negative 0.24. So that's also the row vector, because the about point is 0. And then the tension force, we haven't calculated that yet. A force in the direction of that cable force is what? You need a unit vector. So the point where the cable attaches to the wall, that's the destination of that point, is 0, 0.24, negative 0.48, and the place where it connects to the disk is 0.480, negative 0.24. So you get positive 0.48, positive 0.24, negative 0.24. And now we just have to make that a unit vector. So what do you get if you normalize that? Oh, wait, I know. 0.816, 0.408. What? For which one? Yeah. So this is the point on the wall. That one makes sense, but this one doesn't. Is that right?
The point on the wall, the z direction is negative 0.4, not negative 0.48. It's a little off in the midpoint.
Oh, yeah, you're right.
So I got 0.24 and then negative 0.4.
0.2. Where it connects to the disk.
Where it connects to the wall. That's the first.
Oh, I see. The wall, okay, right. I just drew it. So this is supposed to not go all the way to the end. You're right about that. Okay, so this should be 3.6. Is that right?
1.6, right?
So we're going from,
The middle. Oh, your origin.
so 0.24.
Yeah.
Okay, you went to a different origin.
Different origin.
0.4. 0.24 plus 0.16.
Point. 0.24.
1.16.
Yes. Yes. Thank you. Okay. Okay. And now I don't know what this is anymore. Can someone tell me what that unit vector is?
Negative 0.48, 0.24. Oh wait, sorry. Negative 0.857, then 0.429, then
Positive, positive, negative.
Negative, positive, negative. Just the x should be negative.
Yeah, 0.48 up top should be negative.
Negative, positive, negative. Okay. And so then that force vector is just this times t. So negative 0.857 t, positive 0.429 t, negative 0.286 t. And then what's that cross product?
0.103, 0.343, and 0.206.
Okay. And then the last force we have to deal with is the reaction at pin B. So that is at 0, 0, negative 0.48. That's right, right?
Yeah.
Yes. Got one right. The about point is the origin. Row vector is 0, 0, negative 0.48. The force vector, there's no x component. Oh, there is an x component. There's no z component. So RBX, RBY 0. And the cross product is positive 0.48 RBY, negative 0.48 RBX, but then but Y is always the weird one. So this is right, right? Okay, so Newton's second law. But these are right, correct?
It's negative 0.48 times RDX. That's positive 0.48 RDX.
But then it's like, remember it's,
Negative minus negative, then you're negating it.
yeah.
Okay.
Okay, so Newton's second law. Says RAX, RAY, RAZ plus 0, negative 294.30 plus negative 0.857 T, positive 0.429 T, negative 0.286 T, plus RBX RBY 0 is equal to zeros. And the rotational equation says negative 70.6, 0, negative 70.6, plus 0.103t, 0.343t, 0.206t, plus 0.48 RBY, negative 0.48 RBX, 0 is equal to zeros. So you have 1, 2, 3, 4, 5, 6 equations and 6 variables. All right, so equation 1 says RAX1, T negative 0.857, RBX1, everything else is 0. Second equation says RAY1, T 0.429, RBY1, constant 294.3. Equation 3, RAZ1, T negative 0.286, everything else 0. Equation 4, T 0.103, RBY 0.48, constant positive 70.6. Equation 5, T 0.343, RBX negative 0.48. And equation 6, T 0.206, and then constant 70.6. So could a couple people solve that and let me know when you get answers?
Okay, so we got, for the first one, 48.8, 73.73, 98.4,
Okay.
342.17, 244.9, and 73.54.
All right. Anyone else get that? And then 0. Yay. Any questions about that one? Comments? Angry outbursts? All right, well, let me, we have 15 minutes. What?
We've got, for the R sub AY, we have 2.14.
2?
52.
52?
Yeah, 2.
Anybody, third party, want to weigh in on this?
I got what you have there.
Okay, good. Thank God. Okay. Okay, centroids. So the centroid is the geometric center of an object. And we're going to use centroid calculations for two things. The first is identifying the center of mass of a body. This is such a good quiz question. By the way, like people ask me like how to know. Anytime I make lists like this, I make a lot of quiz questions on those. If I enumerate things, okay. So identifying the center of mass of bodies, and in order for this to work, the body needs to be homogeneous. In order for the center of mass and the centroid to be the same thing, homogeneous means that it's the same material everywhere. So, like for example, the centroid of a hammer is not the same as the center of mass of a hammer because part of it's wood and part of it's steel, you know. But if the hammer was all made out of steel, then the centroid, the geometric center, would match up with the center of mass. So we're going to use, since we're normally dealing with homogeneous bodies, we're going to use the centroid calculation for center of mass. And then the second thing we're going to use it for is treating distributed loads as point loads. And really, these are the same thing. The reason that the center of mass is where it is that the weight of an object isn't really concentrated at the center of the body. It's distributed. A little infinitesimal amount of the weight is located at every part on the body. And when you combine those all, you end up being able to treat that distributed load as if it acts in a single point. So really, number one is kind of a subcategory of number two. But these are the two kinds of problems we're going to use. And the integral definition of the centroid and we're just going to do centroid problems in 2D. X bar, y bar, that's the notation for the centroid, is equal to 1 over the area of the body times the integral over the entire area of x, y, dA. So this is the definition in 2D. In 3D, it looks similar. This is going to be the one we're going to use. But in 3D, the definition looks like this. X bar, y bar, z bar is equal to 1 over the volume of the body times the integral over the whole volume of x, y, z times the infinitesimal increment of volume. So I'm going to calculate the centroid of a triangular shape using this integral definition. But we're not going to use the integral definition for the most part in this class. We're just going to use formulas. And these formulas come from using the integral definition once, and then you can, from that point on, you don't have to do it again. You just use the formula. On D2L, there's a list of formulas for the shapes that we'll use. But I just want to show you how this integral formula works. So let's start with a right triangle. Where this distance is b, and this distance is h. It's a right triangle. I'm going to put the coordinate system here. And I'm going to use this integral formula that says the centroid we're looking for is equal to 1 over the area times the integral over the whole area of x, y, dA. There are a lot of, in mechanics, there's a lot of integral formulas that look sort of similar to this. And when you have to use these, the most important step, the trickiest step, is figuring out how you're going to break up the entire area or the entire body that you're looking up into these infinitesimal increments of area. If you choose to break it up the wrong way, you can make an easy problem hard. And once you choose the correct way to do it, usually the rest follows pretty quickly. So this is kind of the key step. How to define dA. So the way I'm going to do it is break it up the same way as in the definition of integrals when you do the Riemann sum of these little strips. So this is one of my little strips, dA. Its thickness is dx. And its height is defined by the height of the top, I should say, is defined by the formula, the function for this line. So if, at any x value, the height of this rectangle is given by this line function, y equals mx plus b. What's the y-intercept for this line? 0, because the line goes right through the origin. And what's the slope? Rise over run, so h over b. So this is just going to be h over bx. And so dA then is equal to h over bx, that's the height of the rectangle, times the width, dx. And now we do have to think about what the centroid is of each one of these strips. What are the coordinates of the centroid of this strip? So our total centroid is going to be 1 over the area times the integral of the centroid of the strip at some arbitrary value of x. If this strip is at the location x, what are the coordinates of, what's the x coordinate of the centroid of that strip? X, because that dx is infinitesimal. That's not relevant. That doesn't. That's insignificant in this. What about y? That's exactly right. That's going to be half of the height of the rectangle. So that's going to be hx over 2b. You can write it like that. And then we're multiplying that by dA. So hx over b dx. And then the last thing we have to do is define the boundaries of integration. What x values are we going to integrate this over? 0 to b, yep. The area is, so 1 over the area is, the area is BH over 2. So this is going to be 2 over BH times the integral from 0 to b of, I'll combine all this stuff. The x component is h over b x squared. And the y component is h squared x squared over 2b squared. So now you can integrate each of these. So this is equal to 2 over BH times, if you integrate the x component, you get hx to the third over 3b. H, I did say h, it should be h. And if you integrate the y component, you get h squared x to the third over 6b squared. But then what, the x, no, the x should be to the third. And then you get that 6 from the 3 that you got from integrating. And the boundaries of integration are 0 to b. So now you can evaluate it over these boundaries. So 2 over bh times the vector. If you plug b in for x, you get h b cubed, but it cancels with one of those b's. So hb squared over 3. And for the y component, plug in the b for x. So you get b cubed on top. It cancels with the b squared on the bottom. So you get h squared b over 6. And now multiply the constant in front. And you get 2b over 3. And for the y component, you get h over 3. Okay, so all that says that for this triangle, so for the y component, you got 2/6, and I just reduced that. Okay, so the centroid is here, where this distance is b over 3. And this distance is 2b over 3. And vertically, this distance is h over 3. And this distance is 2h over 3. Okay, so now we used that integral formula one time, came up with this geometric location for the centroid, and now for whatever right triangle we're dealing with, we can just use these relationships to find the centroid instead of going through the integral. And I'm not even going to go through the other integrals. We're just going to trust the formulas that come from, a similar approach. Any questions about that calculation? Or about the idea? Okay.